In algebra, the Abel-Ruffini theorem states that there is no general algebraic solution, that is, solution in radicals, to polynomial equations of degree 5 or higher with arbitrary coefficients. The theorem is named after Paolo Ruffini, who made an incomplete proof in 1799, and Niels Henrik Abel, who provided a proof in 1823. Évariste Galois independently proved the theorem in a work that was posthumously published in 1846. Interpretation. The theorem does not assert that some higher-degree polynomial equations have no solution. In fact, the opposite is true. Every non-constant polynomial equation in one unknown, with real or complex coefficients, has at least one complex number as a solution. This is the fundamental theorem of algebra. These solutions can be computed to any desired degree of accuracy using numerical methods such as the Newton-Raphson method or Laguerre method, and in this way they are no different from solutions to polynomial equations of the second, third, or fourth degrees. The theorem only shows that there is no general solution in radicals that applies to all equations of a given high degree. Also, the theorem does not preclude the possibility that every higher degree equation has its own idiosyncratic solution in radicals. That is, the theorem does not assert that some higher degree polynomial equations have roots which cannot be expressed in terms of radicals. While this is now known to be true, it is a stronger claim, which was only proven a few years later by Galois. The theorem only shows that there is no general solution in terms of radicals which gives the roots to a generic polynomial with arbitrary coefficients. It did not by itself rule out the possibility that each polynomial may be solved in terms of radicals on a case-by-case basis. Lower-degree polynomials. The solutions of any second-degree polynomial equation can be expressed in terms of addition, subtraction, multiplication, division, and square roots, using the familiar quadratic formula. The roots of the following equation are shown below. Analogous formulas for third-degree equations and fourth-degree equations have been known since the 16th century. Quintics and higher. The Abel-Ruffini theorem says that there are some fifth-degree equations whose solution cannot be so expressed. The equation is an example. Some other fifth-degree equations can be solved by radicals, for example, which factors into the precise criterion that distinguishes between those equations that can be solved by radicals and those that cannot was given by Évariste Galois, and is now part of Galois theory. A polynomial equation can be solved by radicals if and only if its Galois group is a solvable group. Today, in the modern algebraic context, we say that second, third and fourth degree polynomial equations can always be solved by radicals because the symmetric groups S2, S3 and S4 are solvable groups, whereas Sn is not solvable for n5. This is so because for a polynomial of degree n with indeterminate coefficients, the Galois group is the full symmetric group Sn. This remains true if the coefficients are concrete but algebraically independent values over the base field. Proof. The following proof is based on Galois theory. Historically, Ruffini and Abel's proofs precede Galois theory and Arnold's. For a modern presentation of Abel's proofs, see the books of Tignolle or Persic. One of the fundamental theorems of Galois theory states that a polynomial f(f) x is solvable by radicals over f if and only if its splitting field K over f has a solvable Galois group. So the proof of the Abel-Ruffini theorem comes down to computing the Galois group of the general polynomial of the fifth degree. Let be a real number transcendental over the field of rational numbers, and let be a real number transcendental over, and so on to which is transcendental over. These numbers are called independent transcendental elements over Q. Let and let expanding out yields the elementary symmetric functions of the coefficient of n is thus, let be the field obtained by adjoining the symmetric functions to the rationals. because our independent transcendentals act as indeterminates over every permutation in the symmetric group on 5 letters induces a distinct automorphism on that leaves fixed and permutes the elements. Since an arbitrary rearrangement of the roots of the product form still produces the same polynomial, e.g., is still the same polynomial as the automorphisms also leave fixed, so they are elements of the Galois group. So we have shown that, however, there could possibly be automorphisms there that are not in. However, since the relative automorphism group for the splitting field of a quintic polynomial has at most 5 elements, it follows that is isomorphic to. Generalizing this argument shows that the Galois group of every general polynomial of degree is isomorphic to, and what of, the only composition series of is. However, the quotient group is not an abelian group, and so is not solvable. So it must be that the general polynomial of the 5th degree has no solution in radicals. Since the first non-trivial normal subgroup of the symmetric group on letters is always the alternating group on letters, and since the alternating groups on letters for are always simple and non-abelian, and hence not solvable, it also says that the general polynomials of all degrees higher than the 5th also have no solution in radicals. The above construction of the Galois group for a 5th degree polynomial only applies to the general polynomial. Specific polynomials of the 5th degree may have different Galois groups with quite different properties. E.g., has a splitting field generated by a primitive 5th root of unity, and hence its Galois group is abelian and the equation itself solvable by radicals. Moreover, the argument does not provide any rational-valued quintic that has or is its Galois group. However, since the result is on the general polynomial, it does say that a general quintic formula for the roots of a quintic using only a finite combination of the arithmetic operations and radicals in terms of the coefficients is impossible. QED. History. Around 1770, Joseph Louis Lagrange began the groundwork that unified the many different tricks that had been used up to that point to solve equations, relating them to the theory of groups of permutations, in the form of Lagrange resolvents. This innovative work by Lagrange was a precursor to Galois theory, and its failure to develop solutions for equations of 5th and higher degrees hinted that such solutions might be impossible, but it did not provide conclusive proof. The theorem, however, was first nearly proved by Paolo Ruffini in 1799, but his proof was mostly ignored. He had several times tried to send it to different mathematicians to get it acknowledged, amongst them French mathematician Augustin Louis Cauchy, but it was never acknowledged, possibly because the proof spanned 500 pages. The proof also, as was discovered later, contained an error. In modern terms, Ruffini failed to prove that the splitting field is one of the fields in the tower of radicals which corresponds to the hypothesized solution by radicals. This assumption fails. For example, for Cardano's solution of the cubic, it splits not only the original cubic but also the 2 others with the same discriminant. While Cauchy felt that the assumption was minor, most historians believe that the proof was not complete until Abel proved this assumption. The theorem is thus generally credited to Niels Henrik Abel, who published a proof that required just 6 pages in 1824. Proving that some quintic equations were unsolvable by radicals did not completely settle the matter, because the Abel-Ruffini theorem does not provide necessary and sufficient conditions for saying precisely which quintic equations are unsolvable by radicals, for example, is solvable. Abel was working on a complete characterization when he died in 1829. Furthermore, Ian Stewart notes that, for all that Abel's methods could prove, every particular quintic equation might be soluble, with a special formula for each equation. In 1830, Galois submitted to the Paris Academy of Sciences a memoir on his theory of solvability by radicals. Galois' paper was ultimately rejected in 1831 as being too sketchy and for giving a condition in terms of the roots of the equation instead. of its coefficients. Galois then died in 1832, and his paper, Mémoire sur les conditions de résolubilité des équations par radicaux, remained unpublished until 1846, when it was published by Joseph Liouville, accompanied by some of his own explanations. Prior to this publication, Liouville announced Galois' result to the Academy in a speech he gave on 4 July 1843. According to Alan Clark, Galois's characterization dramatically supersedes the work of Abel and Ruffini. In 1963, Vladimir Arnold discovered a topological proof of the Abel-Ruffini theorem, which served as a starting point for topological Galois theory.